All right, folks, in the last lecture we talked about voltage division and what I also like to call cascaded voltage division, in which we actually took application of KVL and then we just expanded that with the current voltage characteristics of essentially Ohm's law, and then we actually were able to derive a method of finding voltages within a circuit directly without having to worry about the current. Well, after taking a look at that and some of the applications of voltage division, now we want to take a look at current division. And very, very similarly to where we're finding voltages with voltage division with no current, we can utilize current division as an application of KCL in order to find currents without considering voltages. So we're going to start off with basically deriving the form of basically the current division tool, and then we're actually going to do 3 examples in which we're actually going to show how we can see current divide throughout the circuit and how we can actually use this tool to find those currents directly. So the big difference though with voltage division and current division is that voltage division can be used with any number of elements within series. Current division is a little bit different, but let's find out why. So right here I got basically 2-node circuit in which we have a current source. Remember, current source is different from a voltage source. This means that this current is going to be driven to be whatever value that would be. If that was 5 amps, then it doesn't matter what these resistance values are. Here, that would be 5 amps just directly. But in parallel with that, meaning that we would have the same voltage across all elements within the circuit, we have R1 and R2, and both of those are in parallel. Now, obviously, if they have the same voltage, then the currents are going to be different. So we have I1 and I2. So basically, IS is going to flow, and it's going to reach these 2 parallel elements, and as we've discussed before, that current is going to split. And it's going to split between I1 and I2. By KCL, I1 plus I2 has to equal IS. Remember KCL, Kirchhoff's current law, states that the sum of all currents about a node are equal to 0, or the sum of currents in equals the sum of currents flowing out of that node. So if we expand I1 and I2 by Ohm's law, knowing that the same voltage Vx exists, positive to negative, across both of these elements, then it would suffice to say that I1 is equal to Vx divided by R1, and I2 is equal to Vx divided by R2. And if we actually wanted to see what the total voltage was, Vx, across both these elements, then we have to actually combine R1 and R2 together. So the combination of both of those is 1 over the summation of the reciprocals, so 1 over R1 plus 1 over R2. And remember, this form right here is for the equivalent resistance of these 2 elements in parallel. I stress that students use this form. But for the sake of developing this current division tool, I'm going to break it down into the other form that most people will see in the book. R1 times R2 over R1 plus R2. That's nothing more than basically just this form, basically reevaluated to an equivalence. I really stress lots of books love to show this form here, R1 times R2 over R1 plus R2. But it's not practical because all it is just another basically equation for equivalent resistance that you need to learn, and I don't want you guys to learn that. I don't see a point in it. Keep the generalized version. This works for any number of elements in parallel. This right here is only working for 2 elements in parallel. I don't really like this, but for the sake of developing this current division tool, we're going to use this. So Vx is going to be equal to the equivalent resistance times that source current. Okay, so if we say, well, if I have Vx and I have Vx all in terms of resistance and current, then I can probably substitute Vx back into the equation for I1 and also the equation for I2. And let's see what happens when we actually go ahead and substitute that back in there. So I1, that's equal to Vx divided by R1, which is equal to 1 over R1, and then times that equivalent resistance times Is. Because remember, this form right here is what we determined down in this portion for Vx. So we substituted this in for Vx. But if we look in the numerator and denominator, R1 actually cancels out. Sure enough, it does. And so once we cancel this out and just basically rearrange the equation a little bit, I1 is equal to IS times R2 over R1 plus R2. Looks very similar to basically voltage division, in the manner that we have resistance in the numerator and resistance in the denominator. That means that the units of ohms cancel each other out. So the only thing we're left with is amps, and that this represents a proportion. But here's the weird thing, is that in the numerator, instead of having R1, we actually have R2. It's the opposite resistance. So here, when we find or utilize current division, I1 is actually, we're going to utilize the opposite resistance in the numerator. Let's see if that's consistent for I2. I2 is equal to Vx over R2. So just like we showed down here, Vx over R2, we substitute in what we found for Vx. So 1 over R2 multiplied times R1 times R2 over R1 plus R2 multiplied by IS. Excuse me. So here, R2 cancels out in the numerator and the denominator. And when we rearrange the equation, I2 is equal to IS times R1 over R1 plus R2. And sure enough, if we concern ourselves with the current of I2, then what goes in the numerator is actually the opposite resistance of R1. So these two forms, I1 and I2, actually appropriately represent basically the current division forms, in which we have basically I1 is equal to IS times R2 over R1 plus R2, and I2 is equal to IS times R1 over R1 plus R2. Now, let's talk about maybe how this would make sense. Why does it make sense that the opposite resistance goes in the numerator? Well, let's just basically add some actual constants to this. So here we got 10 amps that's going to flow into this node. It's going to split between 10 ohms and 3 ohms into I1 and I2. Let's see what we get for I1 and I2 and see if it intuitively makes sense to us. So I1 is equal to 10 amps multiplied, remember, by the opposite resistance, 30 over 10 plus 30. That gives us 0.75 amps. I2, that's equal to 10, and then times 10 over 10 plus 30 ohms. And so with the opposite resistance, we actually get 2.5 amps. 2.5 amps. So I1 here, we actually got more current, and then I2, we got less current from that 10 amps. We got a different proportion here. Does that make sense? Well, let's remember what resistance does, right? Resistance literally resists the flow of current. So if we look at 10 ohms and 30 ohms, 30 ohms resists the flow of current way more than 10 ohms does. It's a bigger resistive value. So that means that there should be less current flowing through this 30 ohm resistor compared to the 10. And if we look at I1 and I2 after we did our calculations, that's exactly what we get. Sure enough, I1 has more current flowing. 75% of that 10 amps, so 7.5 amps. And I2, 2.5 amps. Oh man. So that actually kind of shows that I1 and I2, the forms that we developed with current division, actually work and actually intuitively make sense in terms of their application. But you may be wondering, well, what about if we tack on 3 elements in parallel? Current division only works for 2 elements in parallel. Only works for 2 elements in parallel. Whereas with voltage division works for any number of elements in series. So any number of elements. And remember that we derived that directly from KVL and showed how that can work. So current division, the tool only works for 2 elements in parallel. So what do we do if we actually have 3 elements in parallel? Do we develop a new technique? No, we don't have to develop a new technique. We just kind of manipulate the circuit a little bit to put it into the form that we can utilize current division with two elements in parallel. But for the resistance that we're looking for the current through, we're going to leave that alone, and we're going to combine the other elements in parallel to an equivalence so that we can utilize these forms here of current division. Let's take a look. Maneuvering down to next whiteboard. Bam, here we go. Ah, sweet. All right, so as I promised, got you right here. 3 elements parallel, and let's see here. We got 5 ohms, we got 10 ohms, and we got 20 ohms in parallel. And just like we've shown before here, there's our nodes, only 2 nodes. All elements in parallel. There's no other element in between each of these parallel elements, so therefore it's just a piece of wire. But as I showed before, here, or said before, we have 3 elements in parallel. We're looking for I1. We're looking for that current through the 5 ohm resistor. So in order to actually utilize current division, well, we can't do it with the circuit as is. We just can't. Can't do it with the circuit as is. Let's take that 10 ohms and 20 ohms. We combine those two together, and once we combine those two together, then we can actually manipulate the circuit in such a way that then we can analyze it with current division. So equivalent resistance, 1 over 10 plus 1 over 20 gives us 6.67 ohms. And sure enough, now we've broke down the circuit in such a way that we have 2 elements in parallel. Easy peasy, piece of cake. I1 is equal to 10 amps times 6.67 over 6.67 plus 5 ohms. And that gives us 10 times 0.5714 or 5.714 amps. And that makes sense to have a higher proportion of 10 amps from the source because 5 amps is less resistance compared to 6.67 ohms. So it definitely suffices to say that current division, we definitely intuitively know that this makes sense right here. Now, some of you may already be asking, well, what if I wanted the current through the 20 ohm resistor? Well, then we would combine the 5 ohms and 10 ohms in parallel. But what about if we want to find the current through the 10 ohm resistor? How will we do that? We got 5 ohms and 20 ohms on either side. Now ask yourself this. I said in one of the previous lectures that, remember, it doesn't matter the location of basically these resistances in the schematic. It doesn't. The relationship to each other, 5 ohms to the 10 ohms to the 20 ohms, is dependent upon their nodes. Those nodes determine that relationship. So it doesn't matter if 10 ohms is next to 20 or if 5 is next to 10. Their relationship isn't dependent upon basically their position. We basically could easily say, rearrange the circuit. I could put 10 ohms on this side and put 5 ohms right next to the 20. I could easily rearrange it, but it wouldn't actually change the relationship of those elements together. And by that notion, we can actually we could easily rearrange the circuit and then say, well, in order to find the current through the 10 ohm resistor, all we have to do is combine 5 and 20 in parallel to get into with each other, and that would easily allow us to solve the circuit. So remember that these parallel elements, they can be rearranged, but do we actually need to rearrange them? No, because their relationship of sharing 2 common nodes allows us to combine 5 and 20 if we are looking for the current through the 10 ohm resistor. So keep that in mind. Keep that in mind. All right. Well, one of the things that we did with the voltage division examples was that we showed how voltage kind of like, divided multiple times throughout the circuit. We showed how we could use voltage division not once, but maybe twice in the circuit. And if we wanted to, if the circuit was big enough, we could use it 3, 4, 5 times throughout the circuit and just watch it continually divide. Well, same thing can be said about current. When current actually leaves the source, depending upon how the circuit schematic is laid out, we can actually see that current divide multiple times throughout the circuit. So for the third example, we're going to divide that current not once, but twice. So let's take a look at basically what we're actually going to divide this current into. So check it out. This is a little bit more complex. This time we actually got a 10-volt source. And with having a voltage source, we're actually going to have to find IS directly. We're going to have to collapse down the circuit first and find IS. But connected to that 10 volts is 20 ohms, 25 ohms. But look what we got going on over here. Oh man, we got 35. But then below that 35 are two parallel elements, 45 and 60 ohms. And for this problem, we're going to find IX. So IX, that's the current going through the 45. Let's talk about the definitions of IS, I1, I2, IX, and IY, and actually show how current, or at least talk about how this current's actually dividing within the circuit as is. So what happens is current leaves the positive terminal of the 10-volt source, IS, and it flows through the 20 ohm resistor. But, oh man, it gets to that node right there, and it splits. And it splits between 25 ohms and then a current that's flowing through the 35 ohm resistor. But as that current flows down through the 35 ohm resistor, it hits another node in which two resistances are now in parallel with each other. So what happens is that I2 then splits again, splits between IX and IY. And so what happens is IX and IY split, they flow through the 45 and 60 ohms, and then at this node they recombine back into I2, meet up with I1 to reform IS and flow back into the negative terminal of the 10-volt source. So in order to find IX, we have to first break down the circuit in such a way that we would actually have IS, and then we would be able to find I2. So let's break down the circuit first. Now remember, I always suggest redraw your circuit so that you have a map of what your circuit looks like as you're going through your analysis. So, 10 volts here, we got IS, and if we see right here, sure enough, if we combine these two elements in parallel with each other, then that combination puts that combination in series with that 35 ohm resistance. And so that means that the current flowing through the 35 ohm resistor is actually going to be the current flowing through the equivalent resistance of those two combined in parallel, 25.71 ohms. So we have IS now splitting between I1 and I2, and that more effectively shows what I said what was happening here. I2 splits between IX and IY. Then this node down here at the bottom, it reforms back into I2, starts moving towards with I1 to recombine. So now we actually can see that we have to find IS first, and then we have to find I2. Once we find I2, we're done basically. All we have to do is do current division to find IX. Now, let's take a look at that. All right. So I collapsed the circuit down. We got 17.7 ohms, and that came from combining basically that 25 ohms in parallel with essentially 35 plus 25.71, because remember those elements were in series, the current flowing, where current I2 flows through. Those two elements are in series, so we took that combination and combined that in parallel with 25 ohms. That gave us 17.7 ohms. That puts all the circuit in series. Oh, no, you probably shouldn't believe me on that. Let's take the nodes, right? Let's look at them. Oh, got the nodes right there. Yep. Yep. They're all in series for sure. So IS is just equal to 10 volts divided by 17.7 plus 20 ohms. The source current coming out of that 10 volt source is 0.265 amps. And so IS is equal to I1 plus I2. So going back, and I put this note here with these two stars and a 1 star basically to just kind of like note back to the original circuits. So rewind if you need to, and to take a look at those two circuits that I'm referencing. So this was the circuit that we just got done breaking down. This is the original circuit that we were looking at the beginning. So IS is equal to I1 plus I2. So I2 would be equal to 0.265. So we're going to divide that source current between basically 25 ohms and then the 35 plus 2.751 equivalent resistance in series. Use the opposite resistance, so I2 was equal to 0.077 amps. Now this current, remember this is I2. If we go back to the original circuit, this is the current that's now going to divide again. So we're going to take this current right here, guys, and we're going to maneuver that down as now the current that's actually going to divide. Just like the source current here, we divided that between those two parallel resistive branches. So here I2, that's actually equal to IX plus IY. IX is equal to I2, or 0.077 amps, times 60 over 45 plus 60. Remember, using the opposite resistance in the numerator again. And that comes out to be equal to 0.044 amps. So as we can see here, the source current divided between those two parallel equivalent branches, and then that current flowing through the original 35 ohm resistor then divided again between the 45 and 60. So if we had a much larger circuit, we could continually see these currents divide throughout each element within the circuit. But again, just like I said with voltage division, it doesn't matter how big the circuit is, because the concept of dividing that voltage is the same. It's just more work. So understand, remember again, I say that there's a big difference between conceptual difficulty and then just more work to do. So if you guys can understand how to do current division twice, you can do it 5 times by just analyzing the circuit appropriately. So for what you guys need to be going through, there's a packet that I've put basically on eLearn under course content about basically how it's like multiple voltage and current division examples. I want you guys to be following through with that, along with the homework that I've listed. And if you guys can understand how to do voltage division and current division multiple times throughout the circuit, then you're probably going to be ready for test 1. So keep working on that. Come to me for questions. See you next time.